on the fourth days of our international virtual courses on the introduction to volcano monitoring using recent technology. So today we are very fortunate to have two prominent research on GPS deformation, Dr. Irwan Meilano and also Dr. Endra Gunawan, which will give us, I believe it will be very insightful on the GPS monitoring for volcano. So we have two sessions. The first, Dr. Irwan Meilano will present his current work on volcano monitoring. And the second session, we will have Dr. Endra Gunawan. So each presentation and the discussion will be around 1 to 1.5 hours. So in total, we will have 2 to 2.5 hours for today's session. Okay, so first I would like to introduce the first lecturer, Dr. Irwan Meilano. Right now is the Dean of the Faculty of Earth Science and Technology. And I received a long list of his research and publication. If I read, I'm afraid that I will steal your 15 minutes precious time. So without further ado, I will give the time and screen for Irwan Meilano to present his lecture on the volcano monitoring using GPS. Please, Pak Irwan.
Okay, thank you, Dr. David, and thank you, Dr. Fahriza, for your kind introductions. It is my pleasure to be here to share my experience in volcano deformations monitorings. And I'm very delighted that today I can meet so many future scientists, good students from not only from ITB, but also from other university, but as also mentioned by Dr. David, from other countries. I will share the informations about deformations monitorings together with Dr. Indra. So I will give for the first, let's say maybe 30 to 40 minutes explanation, and we'll detail explanations. Let me difficulties if I had sometime I had internet connections problems. Just you can really hear my voice. If there is a shortage in my slides, okay. Let me try to share my slide first. Okay, Dr. David, please give me a feedback. Can you see my slide?
Yes, I can see it.
Okay.
Yes, I can
good.
see it.
Okay, it's very good. So these slides been prepared together with Dr. Endra and other scientists, including also Dr. David is. And this research partially supported by ITB and also USAID under partnership for enhancement engagement in research peer science programs. So I'm very glad to be part of this research activity. There are three parts of my talks today. The first one I'd like to share with you the concept, the basic idea of volcano deformations monitorings. I think more detailed explanation will be explained by the next presenters, or maybe some part already explained by previous lecturers. And the second part will be about Sinabung volcano for the last 3 years, or maybe more. Since 2016, I've been working with VSI try to understand the mechanism of Sinabung volcano eruption by using GPS data. And the last part will be I'm going to share my experience when we install GPS instrumentations around Agung volcano. And the last part will be more about discussions. And I always fascinated by volcano. Maybe one of the reasons why I have a very strong interest in volcano, maybe I was born on the flank near of volcano, the Lembang town, and my village is the last village before have experience experience to climb Tangkuban Perahu Volcano. You may find my village is the last village Jayagiri before you enter the volcano. So I spent my elementary school very near to that volcano. So I'm very fascinated by volcanic observations. And another reason, movie 1990, 1997, that movie one, but not interested in that movie anymore. And this is this for the eruptions. And one of the interesting quotes by Prince Borston at the time, he said that I've always been better at figuring out volcanoes than lakes. He said, well, I'm not sure that he is 100% right, but figuring out volcanoes is probably more difficult compared to understanding the politics or people's maybe, but or maybe this problem are difficult. So maybe this problem has the same level of difficulties. Well, I'm not sure, but I always fascinated by volcano-related movies, and this one is I always recommend to my students. And let me continue with the try to shows and this from 2000 until 2016 as you for the country like Indonesia, the number one most frequent disaster is extreme weather. Years we have a flood in Indonesia. I think I have problems. I'm not sure because I cannot see my face. Pak David, until
I think the connection is a bit low, Pak Irwan, because sometimes
let me
I heard
change my connection to.
Yes, sometimes I feel there is a delay.
Let me change.
Yeah, okay. Okay, apparently Pak Irwan has still has a problem with his internet, so hopefully that he will come back soon. So I would like to inform you that for participant, if you have question, you can write down the question in the chat box here, or we will have also a special session for Q and answer question session. You can ask them directly as well.
Pak David, how about now? So I, so I change into a mobile phone connections.
Mhm.
I hope this time is better.
This time is better, Pak Irwan.
Probably I think I need to turn off my videos first.
Mhm,
Okay.
mhm. This time is better. It's much better, Pak Irwan.
Okay. Okay. I hope. Please give me feedback if I have another internet connection problems.
Yes.
So this simple statistics showing us that understanding disaster in Indonesia is very important. And the good news about the volcano eruption is now we have less frequent disaster of the volcano. It doesn't mean that we have a less volcanic activity, but in terms of disaster, we have a less number of disasters for the volcano compared, for example, with the earthquakes. And the reason why we have this data is because since 2000 we have a better observation network, and we have to thanks the VSI Volcanical Survey of Indonesia, who has done a very good job in monitoring volcano activity and giving timely warnings to many Indonesians. So, in terms of the disasters, the number of volcanic disasters is become less since 2000s. But in terms of the direct economic losses to the disasters, we can see that almost every year, 1.2 trillions the economic losses to the volcanic activity. So 1.2 Indonesian rupiah trillions is quite significant. In average, 1.6 billion US dollars per year needs to spend. Indonesian government lost about 1.6 billions every year direct economic losses due to disaster. But if we calculate the indirect effect of the disaster, I think the number is maybe will be double or maybe triple. So understanding the volcanic activity is very important, and one of the method of volcanic monitoring is by using deformation approach. These photos was taken during a leveling observations in 1927. So the volcano deformations monitoring has been established 100 years ago. This is very simple approach, but indeed this is very powerful, and scientists still use uh, this simple approach to observe the volcanic activity. And as you can see that this is a leveling approach, leveling method. We need to have a kind of leveling instrumentations, and someone hold this leveling bar, and we need to take a walk at least 5 to 10 kilos per days to observe the deformations due to the volcanic activity. This is very simple and has been done since 100 years, and many scientists still do this kind of observations. I'm not sure in Indonesia, but in many countries, many scientists still observe the volcanic activity by using these simple observations. And this is examples of how powerful this simple approach. As you can see that this is data from Mimatsu in one of the volcano in Japan, Sowa Shinzan lava dome, and this figure was published in 1962, and this black color shows black color shows the baseline data, the data before the eruptions, and then gradually you can see that from May up to September members, this ground surface uplifted, so gradually increasing the level of the surface of the ground deformations and level of the surface of the ground, and this is good evidence of ground deformations, and this activity has been observed before the eruptions. And another example is the EDM observation, electronic distance measurements observations before the St. Helens eruptions. The movie that I mentioned earlier, the Dante Swix movie, explains the process of volcanic observations and evacuations before the Mount St. Helens eruptions, and it is very interesting to see that this is the flank of St. Helens, the summit of the St. Helens mountain, and you may see that gradually we can see the bulge. For example, this is the contour of 50 feet, and you can see in the less than 1 month, from 7th of April until 1st of May, you can see that suddenly you have a significant bulge here, more than 160 feet, and another bulge also appear here, and prior to the eruption. So understanding the volcanic deformation is give us a very good insight of volcanics activity. So we strongly recommend to observe the volcanic deformation even by using a very simple observation approach. This is another leveling observations near the summit of Kilauea volcanoes in Hawaii. The observer here, and he put 3 observation rod, the leveling rod here, and by using the leveling instruments, they observed the vertical changes due to the Kilauea volcano activity, and this photo was taken in 1981. And the approach of leveling observations indeed is very simple. So if we strong enough to put at least through instrumentations 2 rods between one leveling instruments, then we simply observe the height of each instruments, forwards observations, V as the forward observation, and B as the backward observations, and we can simply doing by using simple arithmetics, we can easily calculate the height difference between each point, and by using several time series, several data with different time windows, then we can have a time series of volcano deformations. And as simple as that, and as an example, this is volcanic deformation observation. I think this photo was taken in sometime in 2004. I think I was first year or second year of doctoral students, and every April we did while seeing the sakura blossom, we did a leveling survey, and you can see that our leveling route is about 20 kilos, and we need to finish all the observation in 3 days or 4 days. So we did the observations, and one of my friend Murase published our data, and it is 10 years observations or more. And finally, he detect an uplift before the eruption. So finally, we have an eruption. If there is no eruption, that how come we interpret our results? But after waiting many years, so we have a small phreatic eruptions on Ontake volcano, and we can show them that before the eruptions we detect significant deformations. The red bar show the uplift, while the blue one show the subsidence. So it's the data from 2004 April until 2006 April. So it's 2-year observations. We did the observation every years, and this is the data from 2006 until 2009. This is 3 years observations, and we can detect significant uplift showings by red bars, and then the scale is only 5 millis, so the maximum uplift less than 2 centimeters. So we can successfully observe the uplift in Ontake volcanoes. And not only observing the uplift, but by using the leveling data, we can produce the volcano source models. And for example, for the Ontake volcano, we propose two models. The first one is we propose two sources. The first one is the dike intrusions, depth dike intrusions, and more shallow dike intrusion. So this is a very good example how powerful the leveling method to observe the volcanic activity. Okay, let me continue my discussions into another approach, the GPS observations. Pak David, I just want to make sure that my connection is okay, still okay. So
It's still okay, Pak
I'm
Irwan.
relieved to see your face, Pak David. Okay, okay.
It's still okay, Pak Irwan. It's perfectly okay.
I'm very happy to see your face moving. Then everything is fine.
I have to
Okay.
keep moving, right? Okay. Yes.
Yeah,
It's okay, Pak Irwan.
yeah. Okay, and nowadays, GPS or GNSS, global navigation satellite systems, become very popular approach to observe the volcano deformations. Not only GPS, but also the GLONASS, but also Galileo, and so many countries already launched their own global navigation systems. And basically, there are two kinds of data that can be used by using the GNSS, the depth data and the phase data. But if you want to get the very precise time series, then we need to use the then we need to use um, uh, okay, I just see the message from you. Okay, it seems to be okay. Then we need to use the phase data. Okay, this is the example of GPS observations. Not in the volcano. I try to find out my data on the volcano, but this time I'm not very successful. Maybe those photos can be shown by Paendra. And this is a GPS observation. This is a typical GPS observation. So for the GPS, we need to have a benchmark here and a GPS antenna. Actually, this is a GPS observations in Calang, west coast of Sumatra. One of the school destroyed by 2004 tsunami. So, but I just want to show you how we conduct the GPS observation, and we need the power supply here by using battery, or we can use solar panels and so on. So basically, this is a typical GPS observations. And this is results of GPS in one of the volcano in Japan, Miyake-jima volcano, and this is my master thesis. We did GPS observations in Miyake-jima volcano. We installed several GPS points there, and as you can see, this is June 26th of June, and this is 27th of June. This is only 1 day observations. 2000, yes, and it is very interesting to see how these islands move. The stations in the north side move to the northeast, while the stations on the south side move to the southeast. So it seemed that the island was stretching, And then and it is very interesting that only less than 24 hours we can detect very huge deformations. You can see the scale is here, 10 centimeters, and so these points move more than 20 centimeters. Okay, and this is one of the good example how powerful GPS to observe the volcano deformations. And I divided the deformation into three phases, and this is the first phases. First, I think the blue was the model, so the locations of the earthquake. So we can see that it is very good fit between the locations of the earthquakes with the locations of the dikes.
Pak Irwan?
Yes.
It seems that little bit connection with internet connection.
Okay. But now is still can hear.
I still hear a delay between the voice. Pak Zul, can you confirm?
Okay.
Yeah, it little bit delay. A voice.
Well, for myself, I think it is very nice to see how we can monitor the volcano activity or the movement of magma that lead to the eruption using the GPS. From presentation from Dr. Irwan Meilano, apparently he is now trying to join us back.
Pak David.
Morning, Pak Irwan.
I'm back. Okay, I will work harder to make chat. I can share all the slides within very short period of time to save the bandwidth. Okay, this figure shows the relations between the earthquakes, deformations, and also the dike intrusion. So I just want to show you that first in the first phase we have a dike here and also the earthquakes. The second phase, second dike appear here, and the third phase we have a bigger dikes at the same locations and also follow also by the earthquakes. And then so let me continue with the discussions from Sinabung volcanoes. So Sinabung volcano is located here. This map just to show you the locations, Sinabung volcano and also the Agung volcano. On February 19, 2018, Mount Sinabung erupted again explosively and destroying the lava dome and producing a new craters. And this eruption is the largest eruption since Sinabung volcano was active again in 2010. And in order to analyze the process of the eruptions, we process GPS data around the Sinabung volcano, and we only process 7 minutes data. So in order to understand the February 19th, 2018 eruption, we just only process 7 minutes data. And this map show the locations of the Sinabung volcano and several thrust type earthquakes and slag slip earthquakes near the volcano. So we process the GPS data, two continuous GPS data. We are very lucky to have the data from VSI, Volcanical Survey of Indonesia, and we process all this data by using a kinematic approach. So we assume that at this point, the SNBG as a stable point. So we observe the motions of another points, MRDG, relative to, with respect to SNBG. So we observe the 2 points, the motions of those points relative to SNBG, MRDG and LKWR. So we observe those points relative to the stable point. We assume SNBG as a stable point, and we only process for about 7 minutes. It's very short periods of time just to see how deformation changes in only 7 minutes. And this is the result. This is the example of GPS time series in Sinabung volcanoes. And this is 2 GPS points. As I mentioned earlier, the LKWR, which is located in the north. So this point located in the north, while the MRDG located on the western part of the volcano. So this one is the north, and this one in the west. And this is the EW components, the east-west components. And so to understand these figures, the scale is 1 bar is 5 centimeters. So this is 5 centimeters. And this is the time. This is the time in seconds. So we process every seconds of the data, and the data is only 7 minutes. As you can see that. So the data is quite stable, and then now this point move to this directions. So moving to this direction means that this points moves to the west. The negative is to the west, and again to the west, and back to the east, and stable again. And the same pattern also detected at the MRDZ, move to the west, and again to the west, and back to the east, and stable. And this pattern is very interesting. And this is the north-south components, and the north-south components also show very interesting results. So it seems that this one is quite stable, and in motions to the north and back again to the south, to the north again, stable again, to the south again, and stable. And while another points, the MRDG seems to be stable and suddenly move to the north. And we also try to calculate the baseline changes. So this is the motions of the 2-dimensional motions, the east, the EW to the east-west and to the north-south. And then now we try to calculate the 2-dimensional baseline changes of that points. And this is the result. So it seems that we have, it is stable, and the extension, straining, the extensions and shortening. So the baseline seems to be shortened, and then again straining again, extension again, and shortening again. So it's extension, shortening, extension again, shortening. So we have a very good patterns of the extension and shortening, but unfortunately we don't have any good seismic data to confirm with the seismicity. We can only confirm with only one stations, And I will show the result comparisons between GPS and with the seismic observations. Okay, and then we plot the factors, the motions of that points, and we divide it into 3 phases. So every phase is about 2 minutes. This is 2 minutes, and this another 2 minutes. So 2 minutes, 2 minutes, 2 minutes. So it's very interesting to see that in the first 2 minutes we have a kind of inflations. The black arrow shows the observations, while the blue one is the models. So we have, it seems that we have the inflations, and another 2 minutes we have again the inflations, and followed by deflation. So we assume that locations of the volcanic sources, the volumetric changes come from one of the spherical source beneath the volcanic crater. So because we cannot estimate the location since we only have 2 GPS data, so we assume that the locations of the spherical sources just below the summit of the Sinabung volcano. Probably the assumptions need to be revised, but since we don't have enough GPS data to constrain the model, so we just give an a priori assumptions of the locations. We just estimate the depth and also the volumetric changes. And then this is the results of our modeling. So so we have the inflations at the first phase. The depth is about this is about 1.2 kilometers from MSL, so it's about 3 kilometers from the summit, below the summit. And we have a second inflation, so it's the first phase of inflations, and we have a second phase of inflation, and it is followed by deflations. As I mentioned earlier, this is only 7 minutes data. So if we calculate the daily data, the daily time series, maybe we can detect a more deeper volcanic sources. That's been discussed by Professor Andri Dianugraha when he published his paper in JVGR. I think we can we may assume that we have a deeper volcanic sources, but since we only process only 7 minutes data, we can only model the shallow part, the shallow portions of the source. Pak David, are you still with me, Pak David? Oh, okay, good. Just to make sure. Okay. And this is the seismic data. So I'm very lucky to have one seismic tool just to confirm the relations between the deformations with the seismic observations. I don't have any information related with the locations of the epicenters or the hypocenters, but just to show you that we have. So the initiations of deformation is almost the same with the detections of the earthquakes. From if we compare this data, the seismic with the GPS, it seems that the seismic shows earlier signals compares with the GPS. Maybe the seismic data detect 10 to 20 seconds before we observe the deformations. So that's the thing that we can share from our experience in Sinabung volcano. Okay, let me continue with the Agung volcano, and this part will be explained in detail by Dr. Endra Gunawan. As have been explained by previous lecturers, Agung volcano is the highest volcano on the islands of Bali, and this volcano has experienced an increase in activity since August 2017. The increase in activity is the beginning of new phase after dormant for more than 50 years. And a series of eruptions occurred starting from November 21st, 2007, which caused the closure of the airport, cancellment flight, and so on. So in this research, we detect the deformations before the eruption. So the eruption was November 21st, but we observed data before that to see if there was or there is a deformation signal before the eruption. So that's the idea. That's the reason why we process the GPS data in Agung volcano, just to see the deformations before the eruptions. And this is the result. This is the time series of daily solutions. So in Sinabung, we process 1 second data. So every 1 second, we show one deformations. But for Agung volcano, we process daily solution. So 1 solution per day. So it is almost 2 years data. And then you can clearly see the time series. This is one of these GPS stations. I'm very sorry that the name of these stations is the YKHR. So this station is here, the one in the south, YKHR. So this station, so this is the time series of the YKHR. So it is very interesting to see that we have a stable and suddenly increase in deformation. The scale is 20 milli or 2 centi. So it is about 2.5 centimeters or maybe 3 centimeters increase in deformations in the north component. So it's the points move to the north and become stable. But it is very, if you take a look data in detail, we have a slight motions to the south before moving to the north. So it seems that this point, the YKHR, moved to the south first, and then after that, move to the north. So it's moved to the south, and after that, a few days after, move to the south. So the data tells that it seems that this point changed the deformation patterns. And then we try to understand why the deformation patterns has been changes. And this is another time series from the point SUTR. The SUTR is SUTR. I'm sorry. Okay. I'm sorry. I don't have the map. Because the quality of data is not good, and it's the RNDG. RNDG is this point. And we can tell a very interesting story about this point. So it seems that this point is very stable in the beginning, but move to the south means if it is very good indications of the inflations. Move to the south, even it's very small motion, but we can clearly see the motions to the south first, and again back to the north, from the south and back to the north. So it seems that this volcano increasing in its activity, but there is no eruption at the time. There was no eruption at the time. I think the eruption was sometimes around here. The November eruption is sometime around here. So there is no eruption at the time. And then and after that, another inflation here, move again to the south. So move again to the south again with a bigger magnitude, but back again to the north and deflate again. So deflations again. And then it is very interesting to see that the eruption actually occurred during the deflation phase of this volcano. And I tried to compare several GPS sites, but unfortunately the data is not as complete of two GPS points. This is the PBBN. This is this point here. I'm very sorry, I don't have the data here. Seems a gap, but can see clearly not so clear. We can see slightly motion to the north at these points. So probably this is the eruptions, and the northward motions is indications of deflations. And this is another GPS point, but unfortunately, again, at these points the quality is not good. And this is another GPS point, DKUH, Dukuh, DKUH. Okay, these points move to the south. This point moved to the south. The motion to the south show indications of deflations. So always deflations before eruptions. So inflations prior to eruptions, and after that, a few days before the eruptions, we show a good indications of deflation. It seems that we have probably inflations on the very deeper portions, but deflations on the very shallow portions, probably. So if we take a look all the data, just to compare all the data, so we have inflations here and deflations. This is deflations, and this is the periods of the eruption. So the eruptions occur during the deflations phase of Agung volcano activity. So we try to model the result by using simple approach, just a spherical model. The first we tried to using the MOGI, and the second one using the modified MOGI, the MTIG models. Basically, the MTIG is just modifications from the spherical source of MOGI. So it's more or less the same. Maybe another lecture will describe in detail about this kind of modeling. So there are two GPS sites that give us an indications of the activity, the RNDG and YHKR, RNDG, this point, and YKHR. So this one is moved to the south. It is the inflation period. This is the periods of inflation, and this one is moved to the north. This is the periods of deflations, and this is periods of inflations again. And the eruptions is, I think, along this line. So we have an inflations, deflations, and again another inflation. So I try to model this this pattern of deformations. So we have inflation sources somewhere around here for the phase one. Deflation associated with the eruption. So prior to eruptions, deflations, and after the eruptions, soon after the eruption, we have another deflations, but after that we have another inflations. So we have another inflation. So we have inflations here and deflations on the second phase, and inflations again. And this is our volcanics deformations models, the source model from the deflations. This is a very simple one, but I think if this model may explain our data. So we have the inflation source. The depth of the source is about 8.6 kilos, and we have deflations. The depth of the source is 7 kilos, and we have a very shallow inflations with a depth of 1 kilo. So this is the first phase, inflations, followed by deflation, second phase, and another inflation, the third phase. And I tried to combine, to compare the GPS data with the seismic observation. So because I'm very lucky that for Agung volcano, there are plenty of seismic data. So I try to compare the GPS data with the seismic. This is one of the GPS stations. So I just want to compare the cumulative displacement, showing by the blue lines. So the blue lines come from the GPS, while the red lines is the energy of the earthquakes. But this is only for the volcanics related earthquakes, not the tectonics one. And then what kind of story that I would like to share from this figure is, it seems that we have a significant amount of deformations prior to the eruptions. So it seems that the eruption showing by this one. This is the eruption, the first eruption, and this one is the second eruption. So we have the evidence of the deformations a few days or a few months before we detect the earthquakes. I think that's the informations I'd like to share from today's discussion. Thank you for your kind attention.
Thank you, Pak Irwan.
My pleasure, Pak David.
So it's time to move to question and answer session, maybe, Pak Irwan. So before we are going into the question and answer session, so I would like to thank Pak Irwan for the very insightful presentation. And once of my professor told me that the great scientist was born near the great geological site. And now I know why Pak Irwan is so good in earth monitoring, because he also was born near the iconic Lembang volcano. Okay. Do we have question from the participant? Okay, I got a private message from one of the student in here that she would like to ask a question to Pak Irwan. Please, Rizka.
Thank you for the time, Dr. David. It was a great lecture, Professor Irwan. I would like to ask about how do you differentiate the ground deformation related to volcanic activity other than another source? I think that was my question. Thank you.
How do we differentiate the deformation caused by the in volcano, maybe with the other source, like a tectonic earthquake, maybe? Please,
well,
Pak Irwan.
Yes. Just to confirm, Ms. Rizka is the one who posed the questions. Yeah, just to make sure.
Yes.
Okay. Thank you for your questions. Yeah, if you are familiar with any volcano observation, let's say for example, seismic network, for example. Of course, by using the seismic network, we can easily differentiate different kind of signals. That is from the volcanic A, volcanic B, or from it is a tremors. It is also it is from the earth, from the tectonics earthquake. It has its own pattern actually. But it may take time, not really long time. If we need, of course, experience, but there are several rules of thumb that can easily be understood to differentiate different kind of the signals. One of the for example, the signal to the co-seismic of the earthquake, let's say the tectonic earthquakes, usually this is this kind of the sudden offset. I think I don't have such kind of the signals. Okay, I'm very sorry that I don't have that kind. The sudden offset usually associated with the co-seismic offset of the earthquakes, and then that can be easily recognized by detect the offset, and the second one by using the pattern of the offset. I mean, if you have several GPS stations located from different area, then we can easily see that this pattern is caused by the co-seismic of the earthquakes, or this is associated with the volcanic activity. And another sources actually come from the atmospheric effects. That's something that needs to be analyzed during the GPS data analysis. But that also can be models. We can easily model the effect of the atmospherics by applying the atmospherics models. Then we can correct the atmospheric effects. Of course, you pointed out very important issues that we need to make sure that this signal is come from the volcano activity, not from other sources. Otherwise, that we cannot analyze the activity if we cannot remove or we cannot understand the signals from different sources. Yes, that's very basic. Then I think that's the thing needs to be studied, needs to be analyzed before we come up with the time series. I hope I answered your questions, Ms. Rizka.
We have also a question from 3 participants. Pak Irwan, we have a lot of questions here. So I would perhaps I would like to deliver the question from Adinda, in which she asks Pak Irwan how to know the eruption time from GPS data, because she only see inflation and deflation data. So how do we correlate this inflation and deflation pattern to the eruption?
Yes, I just compare the eruption time. So I mean, the eruption is the thing that we can easily recognize, aren't we? I mean, if you're familiar with the volcano activity, actually eruption is the only thing that we can see, right? Visually. Oh, the volcano erupting. It is very easy to recognize without any data. But I mean, how to judge the time of eruptions before the eruption? That's different story. I mean, defining that's this kind of this pattern of deformations will lead us to the eruptions. That's very difficult questions to answer. I mean, to know the eruption time is very easy. I mean, one the easiest way, the visual observation. Another way, if you want to just see the seismic record, then we can see the, as I mentioned from the slides that from my slide earlier, it is from the seismic data. We can clearly see that this is it must be eruptions. That's no way this kind of signal is not eruption. That's very easy to detect. But the question is how we can say that this pattern will lead us to the eruption. That's very difficult actually. We need to combine several data. The first, of course, the first data is the seismic data. And then we need to combine the data with the deformations data. Not only the data, but this one needs to be converted into the volcanic sources. We need to calculate the locations and the dimensions of our volcanic sources. And then, so you asked very good questions. Adina, this very very fundamental topics right now is to determine the locations and the dimensions of the volcanic sources in real time. Since we can detect the deformations in real time, so the modelings also can be done in real time, and I think that's the kind of research that many scientists now heading to. So I'm really hope that someone who joined these webinars interested in doing real-time modeling, and which is, I think, theoretically that's possible, and using capability of VSI right now in producing the real-time GPS data. So the real-time modeling is very possible right now. And Pak David, is it okay if I try to answer the first questions from?
Yes. I would like to move to this the first question.
Heruning
Yes.
Yeah, I would like to ask questions.
Yes,
how many reflectors from EDMs will be used to monitor deformations volcano? Well, it is. It is more or less the same. If you ask Pak David how many seismometers needed to get a very good to determine a very good locations of the earthquakes, and that's the same. The answer is always the same, as many as possible. But it is sometimes it is not practical to have so many GPS. As a scientist, we would like to, for example, if we are rich enough, we want to have our GPS or EDM reflectors as many as possible. We put at a grid, for example, every 200 meters, but that's very impractical. I mean, it's very costly. It is very timely to observe. So we need to have a kind of optimizations between money, the time, and also our capacity. So that's always a trade-off between that. I mean, yes, the answer is very obvious, as many as possible, but of course, there are several problems, the logistic problems, and so on and so on. I think we who experience in the field of observations very understand that we always have a dreams to put 100 or 1,000 seismic network, GPS observation network, but well, it is very hard. It's not easy. Okay, Pak David, let me move to the next questions. So how you determine the GPS point? It seems that yes, the location of GPS point it's very tricky. I mean, it's always the same with where will be the best site to put our seismic network. It's always the same. Safety is one of the reasons. We can. The basic idea is we need to put in the stable locations. We just want to make sure there is no such a local deformation. For example, local landslide and so on. So we need help from geologists to give us recommendations of stable site away from local deformation effect. That's one. That's our first. That's our first. The first input to find the locations. But what we need to consider different aspect as well, the logistic aspect, and then if we use the GPS, we want to make sure that we can observe as many satellite as possible. So not only satellite from one side, we call it one side geometry. So we need to detect as many satellites as possible. And also, if we use, for example, the solar panel, we need to make sure that we can detect the sunlight without shade from trees and so on and so on. So it's there are scientific reasons, but also there are some practical reasons needs to be considered. And the last questions, the deformation toward the north or the south indirectly indicate inflation or deflation, but does this have to do with the radial locations with respect to the crater or not? It doesn't has to it doesn't has to be related with the radial directions with the volcano crater. It doesn't has to be like that. But the problem is, for example, in the Sinabung volcano, we only have 2 sites. We only have 2 GPS points. So if you are familiar with finding the locations of the volcanic sources, there are several parameters. The locations, yeah. If you are familiar with defining locations by using the seismic data, for example, you need to find the hypocenters, the horizontal locations, and the depth. But also, if you are using, for example, a very simple model, let's say the spherical model, then we need to define the radius of the source. We need to find, at least we give an a priori assumptions of the change of the pressures. And then there are so many parameters. So then we need to eliminate several parameters. One of very good assumptions of eliminations the parameter is the locations, because since the locations usually below the craters, it hasn't to be like that. But with a 50% probability or maybe higher than that, the locations are always below the craters. For the case of Agung volcano, we are very lucky. We are lucky enough to have 4 or 5 GPS. Then we can search more parameters, not only the vertical locations, the depth, but also we can search the horizontal locations. In that case, we search for the horizontal. And for example, in the first phase, the location is not, we found the location is not beneath the crater, is about 2 kilometers to the southwest of the crater. So it's not, because we let we are using the genetic algorithm to find the source, and so we ask them to optimize not only the pressure source, the size, but also we ask the algorithm to find the location. So basically, we can do the searchings. And the last questions, I have some questions, is the direction of movement of the GPS and as directly related to the inflation, deflation, what's the accuracy? Okay, that's a very good question. The accuracy always the issues in the GPS. I think it's always the same in other observation. Let's say the gravity also, the accuracy is always the issues. Well, the good news is, if you are interested in the volcano observations, most of the scientific software already handles the calculations. I mean, the issues of accuracy right now is become better since most of the software use a scientific software, not the commercial one, because scientific software can model different effects, including the atmospheric effects and some multifat and so on. And for the daily solutions, now we can get sub-centimeters quality. In my experience, if I process the data, so my quality is from 2 millimeters up to 4 millimeters for the horizontal, and so usually we have 2 or times worse for the vertical. So the accuracy of vertical is about 8 millimeters to 12 millimeters. So that's based on my experience. Thank you, everyone, for the questions and also discussions. And also, thank you, Dr. David.
Pak Irwan, actually, I have a question as well. I mean,
yes, Pak David.
If you
Yes.
mentioned about the accuracy of the GPS in the order of 2 to 12 millimeter,
Well, yes.
Could you please tell us about how big is the dimension of the subsurface deformation that we could detect using the GPS?
Well, that's the daily solutions, right? And it if you have a time series, for example, if you have let's say for this Agung volcano, we have 2 years data, so then we can detect the trends. So not only one point to another points, but we can use, for example, simply linear interpolations, or maybe we can use another approach, or if we have a good data set, then we can remove some error or bias by using the Fourier transform F into frequency domains. And so we can place many approaches, Pak David, actually, if we have a very good time series. So I've done several approaches, and basically we can, if you have a consistent time series, I think the similar approach in time series analysis of seismic data also can be applied to GPS time series. So to answer your questions is, how big is the signals or deformation signal that can still be detected by the GPS? So based on my experience, actually, there are several stories that I don't analyze yet. For example, I'm very curious with this one. What is the meaning of this one? It is very short, but it is very interesting to detect. It is a limit. The deformation still in the limits of the quality of the GPS. I think this is less than 1 centimeter. So it's I cannot conclude this time right now because I need more time to analyze the time series. But to answer your questions based on my experience, for the horizontal, we can detect better than 1 centimeter, Pak David. But for vertical, we need to have a deformations at least 2 centimeters or more. So basically, the horizontal give us better detectability compared to the vertical.
Okay. Thank you, Pak Irwan. And
my pleasure, Pak David.
Actually, it's very interesting. And how about the location of the source in relative to the station position? I mean, if it's down below the station, maybe the effect will be different. With it is slightly offset to the right or to the right. Is that correct?
Well,
Irwan?
yeah, that's that's the next stage. Okay, the first stage is defining the patterns, of course. Yes, I mean this is the first one, and then it is a must for us to understand the signals processing, signal analysis, just to make sure the thing that's being asked by Miss Rizka, just to make sure that we detect a correct deformations. I have several experience that actually the deformation is caused by very local effects, but then we need to remove this kind of motions. So that's the first step. And the second step, which is very challenging and it is very important, is to understand. And there are several approaches. This using, for example, this elastic half space model. Using it is it's a very old model published by Mogi 1958, and Mogi used the leveling data around Sakurajima volcano in the south of Kyushu. And this model is still powerful. This model updated 3 years after by MT, and he just give an additional detail. But actually, I have another model by using the Okada, the dike intrusion models. So, I mean, of course, the deformation decay as a function of distance, Pak David. Yeah, as usually we have a kind like this. So this is the R. This is the D, the deformation. So So it may decay as a function. So if we have, for example, the GPS station located far away from the station, then the signal must be very small. For example, I'm not sure, maybe GPS point here, maybe. Well, that is not good example. I will give you a better example. Okay, this one maybe, I hope it may give you a hint. For example, this is the source is here, the dike intrusion, and it's the earthquakes. And you can see the deformation here is much bigger compared to this one. And it may explain these figures, the decay, this is the R, and this is the deformation. And this pattern is very important to constrain the depth of our source, the depth of our source. So it's very simple mathematical relations, but it is very powerful.
Thank you, Pak Irwan. We do have one more question from Pak Ghazali.
Yes, that's a very good question, Pak Ghazali, Mr. Ghazali. Forecasting eruption, yes, we can. I mean, that's the idea, Pak Ghazali. I mean, that's the dream of every volcanologist. I'm not consider myself as a volcanologist, but at least I'm Earth scientist. So that's the dream of every Earth scientist, to forecast something. So maybe you understand that the mediocre scientists describe something, but the best scientists forecast something. So it's always our hope to forecast. But in order to have a better forecasting, we need to understand past data, past eruption. For example, Pak Ghazali, this simple result give a very good indications, because this is one of the volcanic islands. Yeah, the name is Miyake-jima Volcano, and the port is here, Pak Ghazali. The port is here. So during the evacuations, many people went to the port, and they use a big boat to escape from this small island to Tokyo. It is 200 kilometers from the Tokyo. So this is the evacuations area. This is the evacuations area, and they successfully evacuate about 7 a.m. in the morning. But actually, there are another port here. I think somewhere around here. But this port considered to be difficult to access. I mean, it takes longer time to access this port. But the problem is, when they evacuate from this port, actually the eruption is here. The eruption is very near to the port. So they are very lucky because the eruption is 9 a.m. and they successfully evacuate 7 a.m. So only 2 hours time window. So why they evacuate here? Because the scientists suggest that the source of the eruption is below the Oyama crater, the main erupting fan. But actually, based on our model, magma migrations to the west, and the only way of magma migrations, magma transportation, is by using the dike intrusion. So the eruption is here. So the decision was bad decision. The evacuation was a very bad decision. But the problem is, we get the data. I mean, I published the paper 3 years after. So it's to have a better forecasting, we need to understand the past data. We need to understand the Sinabung volcano 2016 eruptions in order we can predicts the future eruption. So we need more and more data. I think the same questions that been asked by also Ms. Rizka and also many students here. I think having very good data sets is very important. So in the futures we can predict the eruptions. Thank you.
Thank you. We have Rizka raise hands. Do you have another question, Rizka?
Yes.
Mm-hmm.
I would like to ask another question. As you mentioned the decay curve earlier, could you explain about any possibility or perhaps your experience in GPS monitoring the submarine volcano like Krakatau? Thank you.
That's very good questions. I mean, we are not still processing not the GPS one, but the INSAR data, and I hope Asep will explain INSAR in detail. Why we use an INSAR? Because we don't have a good GPS network on that islands, on that volcanic islands, Krakatau Islands, but we are very lucky to have an INSAR data. And I hope I can share you the results very soon. And not now, I don't prepare the slide, but we have finished the analysis, and we found an evidence significant in inflations prior to the 2019 eruptions that followed by flank collapse, and we believe that the flank collapse is the main source of the tsunamis at the time. So to answer your question in short, yes, we can detect deformations in Krakatau volcano prior to the eruptions, but not from the GPS, but from the INSAR data. I'm very happy to have the GPS data, but it's very hard to install GPS network in that islands. I hope I answered your questions.
Thank you, Professor.
Yep, my pleasure.
Thank you, Pak Irwan. Is there any more question from the audience? So as mentioned by Pak Irwan, that there are still more research that has to be done in the future. And I believe Pak Irwan has a lot of data. So for those who are interested in this talk and who want to study further on this topic, you can contact Pak Irwan. Okay, if there is no question, perhaps Pak Irwan has a closing statement before we end the first session and we move to the second one.
Thank you, Pak David. I cannot hear your last statement, so we can finish this one and continue to Pak Indra, or is there anything?
Yes, I mean we are going to move the second session, and
okay.
Perhaps you have a closing statement before we
closing
officially
statement.
close this session.
Well, I'm very glad to be here with all the students and mentioned as been mentioned by Pak David Sahara. So we believe that in the future, combining the seismic data with the deformation data will be the futures of volcanic observation. So we believe that combinations of those approaches will be very powerful. Not only the GPS, but GPS also need combinations of the seismic data. And we really hope these kinds of collaborations among students and among researchers will help us to forecast the and ultimate goals is to give a better warning to society.
Okay, thank you, Pak Irwan. Let's give a big applause for Pak Irwan and big thanks for his very insightful presentation and the discussion. Okay, so we will shortly move to the second session, which will be given by Pak Indra Gunawan. But before we move to the second session, and also to avoid the Zoom fatigue, I would like to invite you to move your body. So we will have a break of 5 minutes, and we will start again in 15:30. So don't go anywhere. We still have another prominent researcher in GPS deformation.
Thank you for your kind
So
attention.
see you again very soon.
Pak David, while moving our body, I have a short questions. Pak David, are we going to have a photo session, Pak David?
Yes.
I mean,
Okay, I'm
is it
sorry.
okay to have the photo session right now?
Yes. That will be perfect time. Sorry. Good.
I just
So
want to make
please,
sure
everybody,
that.
turn on your camera. We will have a photo session.
Thank you, Pak Irwan. Of course,
My pleasure, Pak Prof. Andri.
I very enjoy your presentation. Very good. Thank you.
Welcome, Pak Prof. Andri. Looking forward to have collaboration with your student, Pak Andri.
Yes, of course. Thank you, Pak.
Pleasure, Pak.
Dian or Cindy, could you please help us in taking a picture?